Up to now, we have discussed some neural network, basically which predict the output y or predict the conditional distribution of output y for given x. So basically for both purpose, we define some function f with parameter theta, which basically make the prediction y or make the probability vector from your input x. For instance, when you have input image, we pass the input image throughout some convolutional neural network defined with parameter theta, and then predict the conditional distribution for the given input x. And with the true label y from the label, we compare the predicted conditional distribution and the true output y. We define loss function. Basically, usually we use cross entropy. And then train the theta using the training data, which was the typical neural network training process and the neural network concept. And one another important point for this approach was we have a fixed size of input x and fixed size of output format. So we have a fixed number of output classes. So we have fixed dimensional probability vector. Or we just need to make output prediction for a single scalar value. And the output dimension never change, input dimension never change. But in some cases, we have various different lengths of input sequences and output sequences. So the input dimension can vary, and output dimension as well. For instance, if you design machine translator, so if you translate a French sentence to an English sentence, or German sentence to English sentence, usually the sentence consists of different number of words or different number of characters. You cannot define a fixed size of input, you cannot define fixed size of output. So this is one reason why we have to study another concept of neural network. Okay, so from this week, we will discuss recurrent neural network and some variant of recurrent networks where the input has some sequential information and output also can have some sequential information. And the length of input and the length of output can vary. So we have to design some neural network architecture that can deal with such situation. Okay, so machine translator is one application of natural language process. There are a bunch of applications and a lot of researches are going on in this area. And there is a very nice class on natural language process. So if you're interested in this application, please take the course. And this course will just give you very few basic concepts how to deal with sequential information. So basically NLP has various lengths and sequential information. We have to predict something like a YT from the given input x1 through xt, and output y1 through yt minus 1 can be utilized as well. Or you have to design some conditional distribution network which predict yt from x1 through x terminate time y1 through yt minus 1, which basically machine translator require this type of conditional distribution because we usually observe full sentence of input language and then generate the output sentences, and then the output sentence depend on the previous word. So this conditional probability type of output, we will need to design this kind of conditional distribution prediction for machine translator. Okay, so when you look at this conditional distribution part, the conditional part, the ranks of the conditional part vary over time. Each time you will have different lengths. This time as well. So CNN or fully connected neural network is not a good idea in that sense. Okay, so fully connected layer or convolution neural network basically has this shape. There are many hidden layers and you have input and you have output Y. And each layer defined with different parameters like W1, W2, W3, and so on. Each layer defined with different parameters, and so as you increase the number of layers, you have to increase the number of parameters, right? And how to train the deep neural network is very important concept, and we already discussed this thing, right? So when you have very deep architecture, usually the backpropagation suffer from the vanishing gradient and exploding gradient issues. So shortcut is very great idea to resolve this vanishing or exploding gradient issue, right? So this was a very great thing, and we can design very complex function with very deep and wide neural network, and we have shown very fantastic result with LegNet, DenseNet, wide LegNet. For instance, many computer vision tasks like image classification, object detection, we already achieve a very nice result. So many products already in your life. Okay, but this very wonderful network architecture cannot be applied to machine translator because this network architecture is designed for fixed shape of input, right? So we have to think about some flexible architecture so that we can deal with various input size. So we can think this kind of technique. So there is x1 and you predict y1 hat and use some hidden state of the first neural network and then go to second one to predict the y2 using x2 as well. And here our belief is this hidden state abstract all the information on the x1 and y1 hat. Okay, so that this output can model this property. Okay, y3 as well. You can design this network. Okay, so you can think three different functions: f1, f2, f3, with three different parameter set, theta 1 and theta 2 and theta 3, for length 3 input and length 3 output. But as I told you, in this application, our main objective is we want to deal with various input size and various output size. So this can be length 10, this can be length 100, and so on. So for that to deal with such cases, we have to define many functions, and which means we have to define many parameters. Okay, so we need a lot of parameters, right? To define such conditional property, we need a lot of parameters. And also, this is super deep architecture. Why? In a sense, if you want to modeling the correlation between input x1 and output y has 3, the input x1 pass through f1, f2, and f3. So basically, when you focus on the relationship between x1 and y3, this is layer 4 architecture. There are 3 hidden states and 1 output layer. So if the input length is 100, then basically you have 101 layered neural network architecture to model the relationship between y1 and x1 and y100. So this is very deep architecture, especially when you consider a long-term dependency. The very beginning input and the very last output. So without such a shortcut architecture, LegNet or wider LegNet or DenseNet architecture, you cannot well train the long-term relationship because of vanishing gradient and exploding gradient issue. Right. So actually, this is very difficult task to deal with such a various size of input and various size of output. Why? We have to define a lot of parameters, and it implicitly contains very deep architecture. So let's solve this issue one by one. First of all, how can we save the number of parameters? How can we reduce the number of parameters? One very simple and naive idea is, let's reuse the same function again and again. So instead of defining different functions for each step, let's reuse the same function f with the same parameter theta all the time. Okay, same parameter. So x1 here, you estimate y1 hat and use the hidden state x2, y2 hat, x3, y3 hat. When you reuse the same function or same recurrent unit all the time, then you don't need to define all this part. You just need to have theta 1. Right? From this, you can save a lot of parameters. Right? So this is recurrent neural network idea. Okay? So recurrent neural network basically reuse the hidden state and combine with your new input to predict your current output. So this is recurrent neural network. So at each time, you have AT value, AT value, the hidden state value is some nonlinear activation with a weight WAA times AT-1, the previous hidden state vector, plus WAX XT plus BA, and Y hat T is obtained from parameters WAY AT plus bias parameter BY. So this is the most simplest concept of recurrent neural network. Recurrent neural network concept. Here we just need to define WAA, WAX, BA, WAY, and BY. With these parameters, you can handle many different lengths of input and lengths of output. Okay.